Good afternoon, everybody. Get my stuff together here. I want to pin my video. There we go. Let's see. And the chat. Cool. It's good to see the pictures and the videos. Thank you, everybody. I appreciate it. Let's see here. Let me give you guys the frame. There's the attendance document. Go fill it out as usual. And I guess I should just put it out there. Are there any questions? Anything you guys want to see? The room feels dark. Light in here. If I could lift up my monitor, I would totally show you guys outside my window. There's like so much mustard growing. It's really pretty. Maybe I'll figure out how to do that some other time. All right. So, questions, comments, concerns, things you want to cover. Like the chicken? All right. Certainly, definitely talk about linearization. And so I know for linearization, I noticed that Rademacher's, his lecture notes showed something a tiny bit, not so much different, kind of just an extension of the idea of linearization, where you're doing not just the linearization of a function, but the linearization of a vector valued function, which is really just another way of saying a linearization of two functions at once. So let's actually do an example. I'm just going to make something up. Hopefully it won't be too terrible. Sure. So let's do a linearization. Let's use a better pen. I should just throw it. It's hard to throw away pens because you're like, oh, they still got some life in them. So let's do a linearization of the vector valued function. Often this gets a capital, or sorry, a bold-faced typesetting when you're looking at like actual typesetting. But actually, no, he did that in his notes. So if you look at the homework assignment for Rademacher, he has this vector valued function with a bold-faced F. Since I can't really write a bold-faced, we usually use an arrow for vector things. So I'm going to say the vector valued function F of xy is going to equal, what am I going to do here? I don't know. Let's say it's, I like to write my vectors like this. Cosine of xy over, sorry, not over, and then x squared plus y cubed. Sometimes people will think of this as just f1 of x comma y and f2 of x comma y. And what we're really going to end up doing is we're going to end up linearizing both of them on their own. So you could totally treat each of these completely separately if you wanted to, and still get the same result. But the linearization is going to work the same way it usually does. If I'm trying to find the linearization of this function, well, again, it's going to be a vector value function. They're both going to be linear functions. I'm going to think of it like this. It's L1 of x, which is going to be, sorry, of xy, apologies. which is just going to be the linearization of f1, and it's L2 of xy, which is just the linearization of f2. And again, this is a vector, right? There's two components. Okay, so the linearization is just the usual thing, right? So I'm going to actually write this out kind of the long way. So when I'm thinking about the linearization of xy or any number of variables, it's just the function evaluated at the, oh, I forgot to say where. So just one sec. So I'll get to that in a second. So let's say we want to find the linearization of f of xy at, x naught, y naught equal to, I don't know, let's say 2, 0. So I want to find the linearization of the function there. And again, what that means is we're just kind of finding the equation of the tangent plane at that point to these two different functions. So we're finding the equation of the tangent plane to this function, and that's going to go in the first spot. We're finding the equation of the tangent plane to this function, and that's going to go in the second spot. So here's what that's going to look like. Well, the linearization formula is just, well, for L1, it's f1 of x naught, y naught, plus the partial with respect to x. So that's f1 x evaluated at x naught, y naught, times x minus x naught, plus the partial with respect to y evaluated at x naught, y naught, times y minus y naught. All right, that is just our linearization formula. Sorry. I feel like I'm getting some glare from my screen over there. That's what it is there. Minimize that. Okay. And then it's the same thing in the second spot, but for L2. So it's going to be f2 of x naught, y naught, plus f2 partial for x evaluated at x naught, y naught, times x minus x naught, plus the partial for y evaluated at x naught, y naught, times y minus y naught. Now, there's a nicer way of writing this. This is kind of gross. We're going to break this up into this vector, the f1 evaluated at x naught, and the f2 evaluated, f1 evaluated at x naught, y naught, and the f2 evaluated at x naught, y naught. I think I could probably, I'm going to try and fit this down here just so you guys can see it on the same page. This is going to look like f1 evaluated at x naught, y naught, f2 evaluated at x naught, y naught. Those are the two components of that vector. And then all of this is going to look like some matrix multiplication. Matrix multiplication? Or is it a dot product? No, matrix multiplication. Okay, same difference really. So it's going to look like, trying to think about this for just one sec. Yeah, so it's the partial, sure, okay. It's, yes. It's the partial of f1 with respect to x, the partial of f1 with respect to y, times the vector x minus x naught, y minus y naught. And then in the second row, we have the partial with respect to x, partial with respect to x of f2, partial with respect to y of f2. So you see this matrix multiplication, you're exactly going to get in the first row, f1x times x minus x naught. And I didn't write the evaluated at x naught, y naught because it's kind of long. And then plus the partial with respect to y times y minus y naught. And then in the second row, you're going to get partial of f2 with respect to x times x minus x naught, right? That times that, plus the partial of f2 with respect to y times y minus y naught. Over there. So it's kind of long. And then this is called the Jacobian. This f1x, f1y, f2x, f2y. And people might write this as just the function f. So one more even smaller way of writing this, which I know is going to be kind of silly, is someone might write this as, so we'll look back in a second. It's the vector value function. My wife just turned on the TV really loud. It's the vector value function, right there, evaluated at our point, x naught, y naught, plus the Jacobian there, which is just the partials in order. So the first function's partials and then the second function's partials. Oh, sure. No, thanks, Felicity. Great, you guys are on it. Appreciate it. So we've got the Jacobian evaluated at x naught, y naught. And again, that's the 2 by 2 matrix, usually, of partials of F1. People often use F and G, that might have been smarter here. Oh, wow. And then partials of F2. Times the vector x minus x naught, y minus y. Okay, that's a lot. It's a lot without actually having found anything yet. So let's go back to our function and actually say what things are. I'm going to erase this here for a second. So just recalling, our vector valued function f of xy was, sorry, it was cosine of xy and then x squared plus y cubed. All right, so we're at the point, I think it's at 0, 2 or 2, s at 2, 0. Okay, so here, so I'm just going to evaluate things. If I plug in 2, 0, this first part here is going to be cosine of 2 times 0, which is just, let's write it out. Cosine of 2 times 0. And here we're going to get 2 squared plus 0 cubed plus, okay, the Jacobian, that's going to be the partials. So it's the partials of the, so again, that's F1 and that's F2. So the partial of F1 with respect to x is going to be, so the derivative of this with respect to x is going to be negative sine of xy times the derivative of xy, which is with respect to x, which is just y. And then the partial of this with respect to y is going to be derivative cosine of stuff is negative sine of xy times the derivative of xy with respect to y, which is just x. And then down here, we're going to do the partial of this function. So the derivative with respect to x of x squared plus y cubed is 2x. The derivative with respect to y of x squared plus y cubed is 3y squared. And then I'm running out of room. I'm going to erase this. And
James?
Oh, yeah.
James?
Yeah.
For the part that says x squared plus y, is that y squared or y cubed?
It was y cubed.
Oh, okay. Thank you.
And now I'm still evaluating this matrix at the place we're evaluating at, which is at 2, 0. So I'm going to plug in 2 for each instance of x and 0 for each instance of y. And then we're going to multiply that matrix by x minus x naught, which is 2, and y minus y naught, which is 0. Okay, so we're almost there. Cosine of 0 is 1. 2 squared plus 0 cubed is 4. Plus, okay, if I plug in 2 for x and 0 for y, sine of 0 is 0, sine of 0 is 0, so these are both 0. This is a not very interesting Jacobian matrix. 2 times 2 is 4. 3 times 0 squared is 0. And then if you wanted to write this out, so this is kind of a nice way of writing this answer. Like this is how people might just leave it. You could say this is your linearization as a vector valued function of x comma y. But if I was actually going to multiply it out, I would get 1, 4 plus 0 times x minus 2 plus 0 times y is just 0, which I know is super boring. And 4 times x minus 2 plus 0 times y is just 4 times x minus 2. All right, so here's what we've got. We've got that the first function, f1, the linearization for f1 is 1 plus 0. So this is really, really not exciting, but I'm going to write in red over here. So for cosine of xy at the point 2, 0, I feel like I'm No, that's right. Sorry, I feel like I'm making a small mistake somewhere, but I'm not. That should be right. Yeah, sorry. The linearization for this function is just 1. Which, okay, kind of boring. That happens. Yeah, that's totally. No. Sorry, I feel like I'm making a dumb mistake. I just have to double check. Derivative cosine of xy is negative sine of xy times, yeah, y with respect to x. Oh, that's right, okay. And then for the other one, the linearization of this function, x squared plus y cubed, that's going to have a linearization. It's exactly the function we found over there, which is 4 plus 4 times x minus 2. The way I can kind of make sense of both of these is that clearly cosine of 2, 0 is equal to 1. And since it happens to equal 1, essentially your tangent plane is just kind of like so the tangent plane is just the plane z equals 1. So if you change x or y a little bit, it's not going to change the z value because your tangent plane happens to be like a horizontal plane in 3 space. For this one, changing x at least does change things a little bit, right? So if you plugged in, 2 for x and 0 for y, you would get 4 plus 0 plus 0, which makes sense because if you plug in 2 for x and 0 for y, you get 4. But then if you vary x a little bit, you're going to vary this a little bit. If you vary y a little bit, you won't change it because we happen to have picked a value where that's not going to happen. So the linearization here, so back to the other side for just one sec. This really is our linearization. Which again, I will admit is not super exciting, but it is what it is. Are there questions about this?
How did you get from the linearization on this board to the other the other side of the board?
So yes, good question. So here's what I'm doing. I'm really just adding the parts together. So I'm writing it as one vector. So I'm saying the linearization of x comma y is equal to 1 plus 0, and then 4 plus 4 times x minus 2. And this vector is the linearization of each of the functions f1 and f2 as components. So the first linearization is just 1, and the second linearization is just 4 plus 4 times x minus 2. Because again, remember, the linearization of a function is supposed to be a linear approximation. So a linearization of a vector valued function, meaning a function that's got more than one component, is just the vector valued linearization. So each linearization here is the corresponding linear approximation of the original function. So what we're actually kind of saying is we're saying that at the point 0, 2, 0, this function, this vector value function, is approximated by these linearizations, right? Cosine of xy is approximately equal to the linearization in the first spot, which is just 1. And x squared plus y cubed is approximated by the linearization in the second entry, which is just 4 plus 4 times x minus 2. Does that clarify things a bit?
Yes, yeah, thank you.
I will say, this is not going to be the only time we're going to look at vector value functions. We definitely do, I think in section 10, look at kind of really look at systems of differential equations where you've got like 2 differential equations at once, and we write them as differential equation in the first line and differential equation in the second line, and then write them equal to some 2 by 2 matrix times some other vector. So this is not something that's going to go away. So that's why it's good we're talking about it now. Okay, more like this. We can do another one. We can do one that isn't quite as boring as that one. Okay. Now, I will point out, I don't think there's really a good reason for doing it this way specifically. With right, why am I looking at 2 different functions at once? It seems kind of weird, but there might be reasons to do that. So let's say we have this vector value function. It doesn't have to be just of 2 variables, but I mean, a lot of them are. So let's pick, let's pick this one. Let's pick my favorite function, 9 minus x squared minus y squared. And let's look at, what else can I look at? Let's look at, y cubed minus x squared. X to the 4th. It's exciting there. Okay. And we want to find the linearization at the point 2, 1. So all this is allowing us to do is it's allowing us to linearize multiple functions in one shot. So we're not kind of repeating all the same work at once. So here's what we're going to get. Our linearization of xy is going to be our vector valued function. But I suppose I should write an arrow here, right? It's a vector valued linearization. It's going to be the function evaluated at 2, 1 plus the 2 by 2 Jacobian matrix evaluated at 2, 1 times x minus 2, y minus 1. And even though I used F1 and F2 last time, it's probably a little more standard to use like F and G. So if I say that this function is F and this function is G, F of xy, G of xy, or maybe, right, F, okay, fine, whatever. Fine, I'll call it H. Call this one, no, F and G are standard. I'm going to call them F and G, sorry. So what's going to go here is the partial of f with respect to x, so negative 2x, and then here the partial of f with respect to y. Here the partial of g with respect to x. That's a 4, by the way. And here the partial of g with respect to y. So it's always things that are in the top row in the top row. Right, so this is fx. This is fy. It's always the first variable in the first column, the second variable in the second column. And then down here, same sort of deal. Here it's the partial of g with respect to x, the partial of g with respect to y. And then we actually have to plug in these numbers. So here's what we actually get. So f of 2, 1 is the vector. So if I plug in 2, 1, 9 minus 4 minus 1 is 5. And 2, so 1 cubed is 1. Minus 2 to the 4th is negative 15, plus plugging in 2 for x and 1 for y, I get negative 4, negative 2, 4 times 8 is 32, and 3 times 1 is 3, times 1 minus 2, sorry, x minus 2, y minus 1. And you could totally leave it this way. A lot of people probably would leave it this way. If we want to write it out, though, I'm going to write this down here. I can see that the first row, so the linearization of xy is equal to, so the first row is 5 plus negative 4 times x minus 2. Plus negative 2 times y minus 1. The second row is negative 15 plus negative 32 times x minus 2 plus 3 times y minus 1. And what you have in each of the entries in this 2 by 1 matrix, or this vector with 2 entries, in the first entry, you have the linearization of this function. In the second entry, you have the linearization of this function at the point 2, 1. And so then if you wanted to, so I'll give you a second to soak that in. I'm going to erase this in just a moment so I can use the same side of the board still. So then you could ask a question, which we often ask with linearizations, is what do you get when you change x and or y a little bit? So like, what would f of 1.001, sorry, not 1, 2.001, comma 1.03 end up being? And I wouldn't want to actually, I mean, it's not terrible, right? You could totally plug in 2.001 and square it and 1.03 and square it. It's not like the worst calculation in your life, but it's not fun, especially if you're cubing or fourth powering. So instead we say, well, that's approximately the linearization at 2.001, comma 1.03. Because the idea here, once again, is that the tangent plane is supposed to be a good approximation of the actual surface, or surfaces, plural, for values that are close to the place that we are linearizing at, or taking the tangent plane tangent point at. So I'm just going to plug these values into here. So I'm going to get, let's see, 5 plus negative 4 times 2.001 minus 2 is going to be 0.001. And then negative 2 times 1.03 minus 1 is going to give me a 0.03. Same deal down here. Negative 15 plus negative 32 times, it should be the same value there, 0.001. And then plus 3 times 0.03. And we can do the math there, right? It's going to be 5 minus 0.004 minus 0.06. Down here it's going to be negative 15. Negative 32 times 0.001, that's just going to move the decimal over 3 spots. So it's going to be negative 0.032. And then plus 0.09. That ends up being something. This is, I don't know. It's not really important, but it's 4.936, I think. Yeah, that looks right. And this is going to be weirder. It's going to be, I don't know. This is when you use a calculator because your brain doesn't work that well. You get out your calculator and you do negative 15 minus 0.032 plus 0.09. And you get negative 14.942. So that's kind of the idea here. And this is definitely, it's going to do an example like this where you have to do 2 things at once. Again, I erased it, sorry. This matrix.
James, what's the answer for the linearization at the bottom? I can't see the answers. Well, is that 4 or is it 4.936 or?
Sorry, right here? So
yes.
This is 4.936,
mm-hmm.
Negative 14.942.
Thank you.
And I just want to point out the thing I'll say that's kind of about, like, I mean, this is fine. I just want to remind you, the Jacobian is this matrix. We take the partials of the first function with respect to x and y respectively, and then the partials of the second function with respect to x and y. And we'll definitely use that in the future. All right. I had an example here. wanted. Sorry, my examples are leaving me. There you go. So, have you guys started talking about directional derivatives yet? So I know we talked about the gradient. Oh. Yeah, those are the thing I wanted to say, right? You could, if you wanted to, you can definitely think of the rows of this Jacobian matrix as the gradient of F and the gradient of G. So sometimes, I knew there was one other thing I wanted to write. So sometimes people think of the linearization like the real kind of, if you're doing a linearization of some vector valued function f of x, y, it looks like f evaluated x naught, y naught. And then this matrix here, the Jacobian, is really just the matrix of gradients. So sometimes we call it the vector value gradient, like that, times another way you might see your professor write this. So just be aware that that could happen as well. Okay. So what I think is probably worth mentioning now is what's called the directional derivative. And so the motivation for this, I'm going to use my favorite example again, probably going to go down the pages. What I should say first is that the idea of the directional derivative is, right, we've talked about a little bit how the partial with respect to x is the derivative in the direction of x. And the partial with respect to y is the derivative in the direction of y. But there are a lot more directions than just the x direction and the y direction. So, right, we need to be able to differentiate or find the rate of change in directions other than just x and y. And so let's kind of look at my favorite example. I don't know if it's really my favorite, but it's an example I use a lot because it's easy to draw. Ooh, and I might even use, yeah, cool. You'd be smart. Maybe. So, yeah. Let's look at this. So let's look at f of x, y, regular function equal to 9 minus x squared minus y squared. Which I really like, and maybe I was thinking about maybe using Desmos here to show you guys stuff, but let's see. Let's do that. 1 sec. 9 minus x squared. Can I zoom out? Sure. And sorry, no, I'm not showing you guys this just yet. One more sec. I just want another thing. All right, anyway, so gosh, share my screen. Okay. Yeah, let's do it. That's cool. You can just kind of, just so you know, when you share your screen, you can just pick one of your browsers to share instead of like your whole desktop. That's cool. I'm gonna do that. So I guess I'm just sharing this now. Whoops, not that. I blew it already. Things are in the way, sorry.
Will you post the link of this Desmos on Canvas later?
I think it's already on Canvas.
Okay.
But it's just the same one I used before. It's the 3D one there.
Oh, okay.
So if we look at this, this is the surface, which I've been drawing this way. So I'm not drawing all the down part. I'm cutting it off kind of at the XY plane. So it looks kind of like this. The idea is we've got this kind of, this downward opening paraboloid shape. And the idea is, well, we've talked about finding the partial derivatives in the x and the y direction. So for example, and I'll come back to this in my screen again here. If I want to find fx, well, that's negative 2x. And so, sure, and I want to look specifically at the point. I'm interested in what's happening at 2, 1. So if I go 2 in the x direction, 1 in the y direction, if x is 2 and y is 1, then z is 4. I know we've done this before. So we're about there. So there's the level curve, z equal to 4. And right there's the point, 2, 1, 4. Sorry, I'll stop sharing my screen for just a sec so you guys can see what I'm doing better. So there's z equal to 4, there's the point 2, 1, 4. And if we look in just the x direction, so that's moving towards you or away from you. So my derivative in the x direction is negative 2x. And specifically, my derivative in the x direction at this point here is negative 4. So if I think about holding y constant, if I think about this point, if I'm moving in the direction, x direction, well, if I hold y to be 1, right? If I hold y constant as y equal to 1, I've got f equal to 9 minus x squared minus 1 squared. So that's just, so I'm kind of doing this. Right, there's the downward opening parabola that's in the x direction. If I look at the tangent line at that point, the slope is exactly the tangent line right there, which has a slope of negative 4. On the other hand, I should erase that. It's a little too in the way there. Sorry. I can make this work still. A lot of things going on here, I know. So I can see, yeah, it makes sense that fx is negative 4 at 2, 1. And then in the y direction, so that's holding x constant and only moving left or right, because again, right, this is x, this is y, this is z. If I set x equal to 2, I get my function equal to, and again, I'm picking 2 because those are the points that I'm looking at. 9 minus 4 minus y squared is going to be 5 minus y squared. So in the plane x equal to 2, I'm going to get f equal to, or z equal to 5 minus y squared. So it's going to look like, here's a kind of cheat kind of. Sorry, this is a little bit challenging. I'm getting that parabola there, like that. And so at this point, the tangent line looks like that, and it's got a slope of, well, fy is negative y squared. And if I plug in the point 2, 1, I get negative 1 squared, which is negative 1, right? Because the negative comes after the squaring. So the slope at that point in the y direction, when I say in the y direction, I mean in the positive y direction, right? You're moving in a way that y is increasing, just like when I say in the x direction. So in this kind of coordinate system, the y direction means you're moving to the right, because that's the direction y is increasing. the x direction means that I'm moving out towards you because that's the positive x direction. And if I said I wanted to move in the z direction, I'd move up because that's the positive z direction. So moving in the positive y direction at this point, I'm decreasing at a rate of -1 unit per 1 unit increase in y. If I move out in the x direction, I'm decreasing at a slope of -4 units of z per 1 unit of x. But now, from this point on the, I'm thinking of this like a mountain or a hillside. From this point, right, I don't have to move just, out towards you, which is going to take me down the mountain, or right, which is going to take me also down the mountain. I could move towards the top of the mountain if I wanted to. And the question we kind of want to be able to answer is, how do we find the steepness? Sorry, that's really loud up there for me. Right, we were able to find essentially the slope that we are traveling at if in the x direction and the y direction. What if I want to know, what's the slope I'm traveling, going to have to climb up? I'm going to go to the top of the mountain. Or what if I want to, what direction do I need to go if I want my slope to be 0? So I'm just kind of going around and around the circle. And so the idea we're talking about is what's called a directional derivative. Right? I want to find a derivative in a direction other than x or y. All right, so I need to pull up something here so I can look at it. Yeah, okay, good. Come over here, you go over there. All right, good stuff. Let's try this again. All right, so I'm going to draw this picture again. We're going to get real tired of this picture. And here's my XY plane. Oops, that's not Y, that's X. Okay. And if we're looking again at the point, sorry, what do we got here? 1, 2, 4. I think I changed. I see it was 1, 2, 4, 2, 1, 4. I did 2, 1, 4. So that's point 2, 1, 4. It's maybe about right there. Yeah. All right, about right there. And there's the level curve, z equal to 4. And so what I want to ask now is, instead of traveling, in fact, actually, so let's draw, I'm going to draw this circle down here, which is the circle of radius 3. Right? If this is f of x, y equals 9 minus x squared minus y squared. If I set this equal to 0, I just get the level curve on the xy plane, which is 0 equal to this, which is x squared plus y squared equal to 9. So here's the two-dimensional xy plane. And if I'm at the point 2, 1, comma 4, well, I should have done it that way. And it's all right. Sorry, I should really think of this as, I should think of it as apologies. Sorry, I'm going to draw it in red. I know it doesn't really make a difference. I probably could just leave it in blue. But I'm really actually thinking of being on this level curve when z equals 4. Sorry. I'm actually thinking of this being z equals 4, which is x squared plus y squared equal to 5. Right? Because if this is 4, subtract 4, I went over there. And I'm at the point 2, 1, 4. So over 2 and up 1. And right, so it's the point x equals 2, y equals 1, z equals 4. And so far, here's what we've seen. We've seen that if we travel, I'm going to do something smart. Sorry, yeah, of course you are. You should always be using smart. So if I travel in the x direction, well, I should have drawn some more level curves, right? If I draw the level curve, say, where z is equal to 0, and let's do that in orange real quick. Well, that's going to be x squared plus y squared equal to 9. That's going to be the circle of radius 3, which let's say, is over maybe here. Sure. Maybe I did this red circle a little too big. Oh well. So that's going to look like this. And that's z equals 0. So here's what I'm seeing. If I go in the x direction, I'm going down, right? I'm going from a higher z value of z equal 4 to a lower z value of z equals 0. Sorry, one sec. Whoops, oh no, oh no. Okay, I just can't look at myself, it's all right. And if I travel in the y direction, which is going this way, I'm also going down the hillside because again, the z values, the level curves I'm going across are values that are lesser. Right? So I'm moving to a lower z value going down the hill. But I want to know what happens if I travel, in a different direction. Maybe I want to travel in, I don't know, let's say the direction, what do I got here? The direction, oh, we're almost out of time, shoot, I better hurry up. So I want to travel in the direction, I lost my spot. 2i plus 3j. So I want to, from here, instead of going just to the right or just up, I want to go in the direction that's over 2 and up 3. So kind of like, I don't know, maybe like that. I want to go over in the 2i 3j direction. 2i plus 3j is how I would usually write that. Sorry. Okay, so how do we do this? Well, darn it, I feel like I'm going to run out of time here, which is really a shame because we're in a good spot. So here's something I can see. I know my derivative shouldn't be negative because we're still traveling in a direction where we're going to be going down. Right? The z values are going to be decreasing. And the way we can do this is, well, I want to, gosh, we're so close, but I feel like I can't say it. So I'm going to give you the short answer, and then Monday we'll come back and look at the long answer. So here's how you calculate the directional derivative. The directional derivative, which is usually written as d sub u, is the direction you're traveling in of the function f, is going to be given by the gradient of f dotted with the vector u. And I think you do have to normalize u, meaning it's got to be u divided by the magnitude. So we're just going to calculate this right now because we're short on time. And then on Monday, we will definitely do some more explaining. So the gradient here is not too bad. The gradient is, let's see, the derivative with respect to x is negative 2x. With respect to y is negative 2y. And I actually have to, it's the gradient evaluated at the point we're at, which is 2, 1, dotted with the vector u. So the vector u is 2 in the x direction, 3 in the y direction. But then we have to divide by the magnitude of that vector, which is the square root of 2 squared plus 3 squared. So we end up getting, that pen's kind of dying on me. So evaluating this, plugging in 2 and 1, I get negative 2 and, sorry, negative 4, negative 2, oh my God, right? Plugging in 2 for x and 1 for y, dotted with this vector here, which is 2, 3, divided by the scalar square root of 4 plus 9 and square root of 13. When we dot these together, the dot product of two vectors is this times this plus this times this. So that's going to be negative 4 times 2, which is negative 8, plus negative 2 times negative 3, which is negative 6. So I get negative 14 divided by root 13. Notice, and this is important to notice, our answer is just a scalar value, right? We are not getting a vector. And that's always true when you dot two vectors together. Your answer is always something that's just a number. So here's what this is saying. This is saying that if I were to travel in that direction, right, on this surface, which is traveling, 2 in the x direction and 3 in the y direction. So if I go like that way, I'm going to go down the hill with, at least at that point, a slope or a steepness is what we usually say of -14 over the square root of 13. So it should hopefully make some sense that if you're starting at this point here, the direction you travel matters, right? If I go straight towards the center, I'm going to be going up at a positive steepness. If I'm moving away from the center, in this case, in this direction, I'm going to be going downward. But the amount, right, the direction I choose really matters, right? If I go more in the, if I go more in the x direction, I'm going to have a really steep time going down because my slope's going to be super negative. If I go more in the y direction, it's going to be less because it takes me longer to cross down to that lower value. So hopefully that gives you some sort of sense of what's going on. On Monday, we'll definitely talk more about directional derivatives, but this is kind of the real, this is the formula you need to know for directional derivatives. I would like to give you more context for it next time. So we will do that again. A couple last things. Make sure you filled out the attendance form if you didn't already. I'm going to try and get quizzes posted up this week much earlier than I did last week. So once they're posted, I will make an announcement or something so you guys will know that. You'll still have until Monday, but I just thought you guys might like to have a little more time. And I think that's it. For those of you that don't have pictures up today, that's fine, but I would love to see pictures up next time. I like all the pictures. It's great. And all the video. I appreciate seeing your faces. Thank you so much. And have as nice a weekend as you can. I'll see you guys on Monday.
Thank you.
And don't hesitate to, if you
Thank
have
you.
start a discussion on Canvas and someone will answer them or I will answer them or I'll make a video or something. So
Okay.
the more you ask for, the more I will do. Bye.